Hi, so in this video we're going to explain how we can use calculus to find the length of a curve, and by this we mean of course a curve that is given as a function y equals f of x. So I'm going to have a function up here, y equals f of x between 2 points, say a and b. I want to find the length between this point here, a f of a, and the point b f of b. So the approach that we're going to follow is to take this into a sum of tiny pieces and then take the limit, and that will become an integral. So how are we going to do that? Well, as we've been doing learning about integrals, we always cut the domain into subintervals. So I'm going to call this x0 is going to be my starting point. Let me write it backwards. Let's make a equals to x0. It's going to be less than x1, less than x2, less than xn. And for this, we're going to call delta x the differences. I'm going to assume that they're all the same. So delta x is the distance between an xk and an xk minus 1. Okay. So by doing that, we're cutting these. Finding these points, you can find these points here, which are going to be the y's of each of my xk's. Okay, so we're going to call. We're also going to call yk equals f of xk. Okay, so what we're going to do is approximate the length of the curve by tiny segments. So look at what I'm going to see about a little tiny piece around here. Pretend I'm looking at two contiguous points right there, and we zoom around that. It's very thick, but pretend I do a zoom around that neighborhood, and what I see is something like this. I see something like, this is my zoom box, and I see something like a 2 points. It's not going to look like that, but pretend it looks like this, and I have 2 points, one of them right here, which is my point. I'm going to call it backwards. It's going to be xk minus 1, comma, yk minus 1, which is the f value at xk minus 1, and the point over here, which is the next point, so it's xk, comma, yk. And we're going to find the distance between these 2 points. Okay, we're going to call it lk. And that distance is really just a line, a segment. So we can find that by finding this, by making this Pythagorean theorem, this right triangle right here, and just noticing that this length here between this side is just a difference of x values, right? So this segment is just delta x. And the height, so this other leg of my right triangle, this one, is the difference of the y values. So we call that delta y. Now this is delta yk because that one is not constant. The delta x is the same. I can assume they're the same over here. I'm cutting them into pieces, so I could set them equally distanced. So delta x's are all the same. The delta y's are not. That depends on the change in y, and that depends on the function. Okay, but I do have a length formula or a way to calculate lk. So lk, the distance, is just a Pythagorean theorem and apply it to that little triangle. So it's the square root of delta x quantity squared plus delta y quantity squared. Right? That's all it is. So all I have to do now is find a way. Our goal is to find the total length and to say, well, the length that I'm looking for is the sum of my lk's. Well, it's approximately. It's going to be equal when we take the limit. When we take the limit, when the delta x's go to 0 of this sum. So that's my goal to find an expression for this. Now we're not done. Okay, we have a little bit of problem, a little bit to work on here, and for that we need to remind ourselves something called the mean value theorem. So the mean value theorem from Calc 1 said something very simple. The idea is very, very simple if you see this in the picture. This is saying that if you have a function defined in two values, a and b, it's continuous. that the point have to be a continuous function, and I have my function like that somehow. That goes from f of a to b f of b. Let me change my function in the middle just to make this something like that. It doesn't matter how it occurs. I just want it to be continuous, and it joins those 2 points. Then what this says is that there's a point in the middle whose derivative is actually, look at the right side. This right side is really the slope between the points a, f of a, and b f of b, right? This is the difference of y values over the v values. This is this slope, right? And this is the slope. So it's the slope of this red segment that I wrote right there. And what this theorem is saying is very simple. It says that there's a point on the curve for which, I'm moving this slope to be parallel, right? All these have the same slope. So there's a point on the green curve that exactly is a tangent, right? So somewhere around there, there's a point, if you go down here, we call it C, such a derivative of C is exactly that value for that tangent. So that's what the mean value theorem says. And how are we going to use that? Well, we need to use that on each tiny subinterval over here. Okay. On this segment, I'm saying, using the mean value theorem, so I'm not going to write that big, but if I use the mean value theorem in this segment, I have that there is a value, I'm going to call it CK, that is between the xk minus 1 and the xk, such that, I need some space here, so I'm going to make this smaller. Put it over here. I'm going to make this smaller. Put it over here. So using the mean value theorem, there's a value ck on each segment, such that the derivative at that point is equal to the change, the change on the y values, right, over the difference between the x values. So the difference of the x values is exactly what I'm calling delta x. And the difference of the y values is what I'm calling delta yk. Remember, I need the k there because that is different. So then I need an expression for this, right? This is what I want to find out here. So I'm going to find, sorry, that should have a k in there. That looks terrible now. Let me change it. So it should be plus delta yk squared. Oh, sorry, and I want that to emphasize that this is going to be red now. So I can solve for that here, noticing that, oh, so delta yk is going to be f prime of ck times delta x, right? And then I have everything I need to work it down. So let me put these two things together over here. So I found a couple things. I'm going to write it here. Need some space. I have a couple things. That the LK was the square root of delta x squared plus delta yk squared. But we found a way to write this delta y squared like, f prime of ck times delta x. That's what I have over here, right? Delta yk is f prime of ck times delta x. I'm using that inside here, and I'm squaring it, okay? So this, of course, becomes the delta x quantity squared plus f prime of ck quantity squared times the delta x again squared. So here I have the delta x squared on both terms, so I can factor it. It looks like this. Put parentheses right there. And because I have it like this, I'm allowed to separate this square root like this. So the product of a square root, the product inside the square root can be broken up. Not with a sum, but this is a product. Okay? So, of course, why did I do that? Because then this is just a delta x, right? I'm going to write it backwards. I'm going to put this term first. Okay, so I did all the work here to get this expression for LK. So remember, LK is the length of one of these tiny segments. And now we're ready to write this as an integral. So that puts on the side. So now we have that we said that the length was really the limit when my delta x's go to 0 of the sum when k equals 1 up to n of my LKs, but I found my LK to be this expression. So I'm going to write the square root of 1 plus quantity f prime of ck squared delta x quantity squared. No, delta x, sorry. Now, who are the ck's? Well, these ck's is 1 point for each subinterval, right? And that is exactly what we did when we find the definition of an integral. This is, I'm dividing my domain of integration a to b. So this picture is not the picture for this. It may be confusing. This picture is a picture for the mean value theorem. Okay, the picture I'm thinking about is this one. So I'm dividing my interval a to b into tiny segments. I'm picking a ck on each one of these, evaluating it there, right? And if I take the limit as the delta x go to 0, that's exactly when this becomes the integral from a to b of 1 plus f prime. I don't put the ck's anymore. You think of it like f prime of x squared, it's still the quantity squared, dx. So this is the formula we want for the length of a curve. Okay, so let me put that all together. This is the formula that I just talked about. So you have to find the derivative of the function, square it, put it inside the square root, and then take the derivative. Sorry, and then take the integral, antiderivative of that. Now, you can imagine these integrals could get very ugly because I'm going to have an expression with x inside, right? And then I have nothing outside of the root to make it look like make a u substitution. So in order to solve this definition works great in practice. If you grab any curve and you want to find its length, you're probably going to get stuck in how to evaluate it. It have to be very special ones. Now, fortunately, we can use this. Oops, I have a little typo here. What's came in? We can use this to. We know what the length of a circle with radius 1 is. So if I have a circle with radius 1, I can't do this as an entire curve as a one function. So I'm going to focus on only half of it, right? So this is the curve, oops, this is the curve. If I write f of x equals square root of 1 minus x squared, that's half of the circle, right, from -1 to 1. And then what I would want to do is find the derivative of that, square it, put it inside the square root, and use a formula, okay? So that's what I want to do. Now, I'm going to focus in one even more smaller than that. I'm only going to focus on a quarter of the circle, okay? So just from 0 to 1 to 1. Sorry, my circle isn't a circle, but that's what I want to do. So okay, so let's go just try to do this. So this said my function, my formula we found was the length is going to be the integral, in this case, from 0 to 1 of the square root of 1 plus the derivative of this function, quantity squared, and the dx. So I need to find the derivative, I need to square it, I need to add 1, and take the square root of it. Okay, so let's find the derivative. So the derivative is, this is to the power 1/2, so you can put it to the -1/2, times the derivative of the inside, which is a negative 2x. Sorry, I forgot. This is to the power 1/2, so if I do the steps carefully, the derivative would be 1/2 times that to a -1/2, so these twos really cancel, right? So I get this. Okay, so now I need to square this. So let's square it. So if I square it, derivative of f prime quantity squared becomes x squared. I can forget about that negative. And the denominator, I get 1 minus x squared. I can forget about the square root. Okay. Now I'm not done. Now I need to put inside the square root of it. So I need to write square root of 1 minus f prime of x quantity squared. So I would do square root of 1 minus x squared over 1 minus x squared. So I'm going to put it under the same denominator. So I put this guy over 1, and I multiply and divide by this term, right? So I'm going to get 1 minus x squared. Sorry, I put a minus here, and it's not minus, it's a plus. If not, that wouldn't have worked. There you go. Plus x squared over 1 minus x squared. There you go. The x squareds cancel, and I really get the 1 over 1 minus x squared. Okay, so I know what expression I need to integrate now. So I did all this work to find the expression that I need to integrate. Maybe put this in the corner. Now let's find the integral. So my length finally is going to be the integral from 0 to 1. And remember, this is going to only give me 1/4 of the circle, okay? From 0 to 1 of this expression here, which I can write it like 1 over the square root of 1 minus x squared, correct? Why did I write it like that? Because this is, if you look at your table of derivatives, this is exactly what the derivative of sine inverse of x. So this is actually the derivative of sine inverse of x, or this is the derivative of this function is really the inverse function of sine of x from 0 to 1. So you had to do the sine inverse of 1 minus the sine inverse of 0. When is the sine 1? It's at pi over 2. When is the sine 0? At 0. So I get pi over 2, which is what I would expected, because this is 1/4 of the circle, right? And if I multiply that by 4, I get 2 pi, which is 2 pi r when r is 1. So the length equals 4 times pi over 2, which is 2 pi. Okay, so I hope this gives an idea of how to manipulate these integrals and how to find the lengths. So the steps are, just to review for 1, 2, the steps are 1, find a derivative, 2, square it, 3, write this expression, and then 4 might be something like manipulate that to make it easier to integrate, right? If I wrote it like this, I probably wouldn't have been able to find out how to integrate. So it's sometimes better to use a simplification here before you plug it into the integral you need to calculate. Okay.